Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, Identifying Directing Groups and Reactions with Benzene and Benzene Derivatives. Okay gang, so you probably know the worksheet solution walkthrough drill by now, but if you're brand new, here's the little rundown. You've probably seen an instructional video here on jOeCHEM. You've probably seen the associated worksheet practice. If you have any questions about the answers that were provided, well, you're in the right spot. In this video, we're going to go through this worksheet hopefully very efficiently because sometimes these run long, hopefully they'll be fast, and hopefully get the answers that you are looking for so that the practice makes sense, so that you feel cemented in the concepts that you were trying to exercise. But enough of my blabbering, let's get to work. Okay gang, so before we start problem one, you're going to see a giant mess right here. So I'm going to step aside. I'm going to let you, if you want to pause the video so you can take a look at a future reference, please do, because what I'm going to do is to go by each of these one by one would have taken forever. So I threw up everything on the board, and we're going to go one by one on each stop, and I'll explain why I labeled what I labeled. Okay, so remember, with the directing group, so what we were tasked with doing is deciding whether something was an electron withdrawing group or electron donating group. We know we can figure that out by what is directly attached to our benzene ring. Then we needed to determine whether, if it was an ortho-para-director or a meta-director. That goes hand in hand, whether it's an EDG or an EWG, based on the resonance that we've seen work out. And the last thing we had to do was figure out whether it deactivates or activates the ring through resonance or induction, okay? So if we take a look up here, I hope what you're seeing is we have this nitrile, this CN, right? And if I wanted to expand this, right, because we worked with nitrile a whole bunch, that's coming very soon. What I hope you're seeing is this is a very partial positive carbon bonded to nitrogen. The resonance will work such that it brings electrons out of the benzene ring. But even if you wanted to use our rule, which absolutely works, this atom directly attached to the benzene ring is super partial positive. It is an electron withdrawing group, it is a meta-director, and via resonance, it deactivates our ring because electrons are taken out. Subsequent EAS reactions will not be as fast. Next one, right? So I hope what you're seeing is the nitrogen right here has electrons. It can absolutely donate those to the benzene ring via resonance. So it's an electron donating group, ortho-para-director, and it activates the ring via resonance, okay? Now down here, remember, this is one of our induction cases, I'd say. So it's an alkyl group, just plain and simple. So it donates electrons via hyperconjugation. It's an ortho-para-director. It's slightly activating, right? You don't have to put slightly, but just to remind you, it's not nearly as strong as something like NH2 or an O-methyl, a methoxy group. So slightly activating via induction, that's I, right? I'm using R for resonance, I for induction. Moving on. This one I like, it's a little tricky. So up here, this is actually an electron withdrawing group, and it's kind of in disguise. So it's an EWG, a meta-director, and it deactivates via resonance. But, if you look at this carbon right off the benzene ring, that's not super obvious. But the resonance shows you otherwise. We can absolutely show electrons moving out of the benzene ring, making a bond right here. Electrons can move over there, and electrons can bounce up there. So, really, this is a partially positive carbon via resonance in disguise. Okay, I encourage you to draw this resonance on your own. You'll see, even if you just do these resonance moves, you'll see that carbon is a positive, partially positive. This is a functional group called an enone, and we will see those very shortly. So, EWG meta-director deactivates via resonance. Okay, right here. So remember, another one of our inductive cases. So we know chlorine or all halogens are electron donating groups. They direct ortho-para. However, because they're so electronegative and because they hate sharing electrons, right, they suck electrons out of the benzene ring. They slightly deactivate via induction. Okay, so your ring becomes slightly less reactive. Okay, moving on. So we see what is directly off of our benzene ring. We see a partial positive carbonyl-carbon. You're absolutely right. The resonance will work itself out like that. So an electron withdrawing group, it's going to be meta-director. It's going to deactivate via resonance. Over here, same deal. It's just a different flavor of carbonyl, right? We have an ester versus an amide. Absolutely another partially positive carbonyl-carbon. It's going to suck electron density out of the ring via resonance. That's why it deactivates resonance, electron withdrawing group, and it will direct meta, okay? Over here, okay, now we see one of our really, really big deactivating groups, a sulfonyl group, right? Again, attached to the benzene ring, we see a sulfur attached to 3 oxygens. That is a really, really partially positive sulfur. Okay, so it's going to be an electron withdrawing group. It's going to go direct groups meta, and it will deactivate via resonance. Over here, nitro group, same deal, same rationalization. Electron withdrawing group, meta director, deactivates via resonance. That's a super partial positive nitrogen bonded to 2 oxygens. And up here, okay, we see our good old friend methoxy. We use this a bunch as an electron donating group. We know that this atom off the benzene ring has electrons. It is more than happy to donate those to the ring. So we know it directs orthopara, it's a donating group, and it activates via resonance, okay? Over here, similar deal. So you can see how an ester, depending on how it's attached, can be both a withdrawing or a donating group. Here we have what I would call the ether portion, right, of the ester directly off of our benzene ring. It can absolutely donate electron density to the benzene ring. So it will it's a donating group, it directs orthopara, it activates the ring via resonance. And last but not least, we have an amide. Again, you can see it's just attached differently, but here we have the nitrogen with its lone pair directly off the ring. It's going to be able to donate those, and via resonance, it donates electrons to an EDG, directs orthopara, and it activates the ring via resonance. Okay, gang, I'm gonna step aside to let you take this all in again. That's number 1. Hopefully all those made sense. If not, just make sure you're working out the resonance and actually, sit down with it and see how it works out, because you can take my word for it, but it's much more powerful if you see how it works itself out. Okay, gang, so that's number 1. Let's move on to 2. Okay, gang, rolling on into problem 2, part A. So the problem states, and of course I just said, sit down and make sure you rectify the resonance for yourself. We're about to do it right now. So in part 2A, we're told in the problem, methoxybenzene donates orthopara when, subsequent EAS reactions are done with this structure, methoxybenzene. Explain why. So again, remember, this is EAS, electrophilic aromatic substitution. We are putting electrophiles on we're substituting electrophiles onto aromatic rings, okay? So, or aromatic compounds. So, that means electrophile, lover of negative charge. That means something positive like Br+. So Br+ will be attracted to positions where there's more negativity. So, if I redraw methoxybenzene, we'll start from scratch down here, right? We know this drill. You've already seen the video where we've drawn the resonance. That's what we need to do to demonstrate this, to get the points for this problem. So, we know this is an electron donating group, electronegative atom directly off of our benzene ring. It will swing electrons down. We will form a double bond here. To avoid breaking the octet rule at this position right here, I will bounce these electrons up in the double bond over here onto this carbon on the left shoulder, if you will, and make a lone pair. So remember, don't forget your resonance skills. Make sure to draw a double-headed arrow that says, hey, look at me, I'm drawing resonance. So we have a lone pair right here, double bond that I didn't touch, double bond that I didn't touch, new double bond up top, O, CH3. The oxygen now has a positive charge, and this carbon over here has a negative charge. Remember, if we start neutral, we have to end neutral as well. You can't just invent charge. Okay, and now we're gonna play ring around the rosy. So I'll swing the lone pair down, form a double bond. I'll have to bounce this up as a lone pair to avoid breaking the octet rule at this carbon right here. So the lone pair moves over to the bottom position, the ortho position. Because we know how this resonance is going to work out. This is no surprise to us. So I'll just redraw my charges. The methoxy didn't get touched at all. Oxygen's still sporting the positive charge, negative charge down here. And last but not least, I can swing this down, form a double bond right there, and bounce this up as a lone pair on the top right shoulder on the benzene ring. So that it's kind of ugly. There we go. Lone pair right there. Still got the positive charge on the oxygen. So again, what you'll see, right, is remember, we don't ever just look like this, or this, or this, or this. We have a combination of all of them. So you can see that we have partial negative, partial negative, partial negative, and I don't even, if you even wanted to draw that, this would suffice. This would tell someone, you know exactly what's going on here. That's why this group ends up directing ortho-para because the resonance works out to where we activate these positions with extra negativity. The positive things we are going to be substituting on our benzene rings will be attracted to those spots. Okay, gang, that does it for 2A, 2B. Okay, gang, to round out problem 2 with part B, we have a very similar task, except this time we have not an EDG, but an EWG. We have nitrobenzene, and we're tasked with explaining why nitrobenzene directs meta in subsequent EAS reactions. Now, it might be a broken record, but remember, EAS, electrophilic aromatic substitution. We're going to be substituting electrophiles onto aromatic compounds. What are electrophiles? Lover of positive charge. I always have to take a second in my head to rectify what electrophiles are. Nucleophiles, for some reason, are much more intuitive to me. But remember, that's something like Br+, a lover of negative charge. So why do electrophiles gravitate to these positions for something like nitrobenzene? So what I'm going to do is, maybe the hardest part about this is knowing how to expand the nitrobenzene, because we will need to draw resonance. So it's weird because nitrobenzene contains two charges that offset each other, okay? So we have nitrobenzene. We know this is an electron withdrawing group. That's so evident by the fact that nitrogen is not even partially positive charged. It's positively charged. So remember, this will suck electron density outside the ring, which makes sense. We'll have an arrow going up here forming a double bond, and to avoid breaking the octet rule for nitrogen, I will bounce a double bond up to carbon right there. So remember, draw your double-headed arrows like this, saying, hey, look at me, I'm drawing resonance. And then trust your arrows, right? Didn't touch this double bond, didn't touch this double bond. I now have a double bond right here. I have a nitrogen, the same nitrogen. I didn't touch this oxygen over here, it still has a negative charge. And now I have a negative charge on this oxygen. Well, I think I called this a nitrogen, oxygen. Two oxygens with two negative charges. And I still have a positive charge on nitrogen, weirdly enough. Right? You'd almost think it would get something out of that deal. Nope. But remember, we were neutral here, we better be neutral here, and it's because I haven't put this positive charge there yet. So we have a positive charge on the top left shoulder of our benzene ring in the ortho position. So what can I do next? Well, let's ring around the rosy. I can swing these electrons in this double bond towards this positive charge. No need to do any other resonance move. And also at this point, I can still draw this as an NO2, but I'm going to keep it expanded. But just know you could definitely collapse it if you wanted to. I'm not going to draw the lone pairs though. So I have these two double bonds, and the positive charge moves down here to the pair position. And last but not least, we can do one more go around. I can move that double bond down right there. And last but not least, what do I get? I get another positive charge, and it's on the other ortho position. So you can see, remember, we are a combination of all of these resonance structures that combine to make our overall resonance hybrid. So with NO2, I hope you can see there's a delta plus, delta plus, delta plus. So before, remember, those were delta minuses. The positive things we'll be adding in EAS reactions would gravitate to those more. However, with withdrawing groups, we make these positions less favorable, right? So in fact, this bromine isn't super jazzed to go to this position or this position, the two metas, but it sure as hell wants to go there over the ortho and para positions, okay? So this would be plenty to get credit for this type of question on an exam or homework, whatever. Okay, gang, that's problem 2. Enough concept. Well, okay, we're still gonna use concepts, but let's do some complete the reaction questions. Okay, gang, so in problem 3, we have 8 EAS reactions, complete the reactions. These ones, some of them are straightforward, some of them are a little tricky, and there's even more on the next worksheet that has the synthesis involved. So if you left this thinking this is too easy, don't worry, I wanted to build your foundation first to make sure you had some consistent, straightforward problems to do, and then crank up the difficulty a little bit. Okay, so if we take a look here, let's just go right at them. So right up here, we see a T-butyl group. So when you do these problems, I want you to think about the following, right? You know this is an ED, this should probably flash in your head, EDG, slightly activating, ortho-pair director, right? Okay, so we know this is the reagents for sulfonation. We're gonna put on a sulfonyl group, an SO3H. Now, this is a big bulky T-butyl group. since it's ortho-para directing, and when we have, if we were to put something ortho, we would certainly have some steric hindrance, right? Especially with this being so highly branched and our sulfonyl group being pretty big, it's absolutely going to be directed para. So our product looks like this, right? If we can put something para, we're going to do that over ortho first. Okay, now this problem right here. So I like this problem because you might get baited into one position that really doesn't work. So again, right, what do we have? We have two electron donating groups. They will activate the ring. We know that they are ortho-para directors. So we know that they have the same directing power, right? And so we're going to see if we have a common place of directing, right? That we can line up and place this chlorine, because these are the chlorination reagents. So one thing this problem tries to bait you to do is to think, oh, they could both ortho direct right here. However, that will not happen. You will never put, especially if you have other positions available, you will never direct in between two groups, because that's just a recipe for steric hindrance. Instead, I hope you can see, right, this methoxy group, or this one, doesn't matter, we have symmetry here, can direct ortho here, and this one, or sorry, para here, ortho here, right, because 1, 2, 3, 4, para, 1, 2, ortho. So, I know just for further kind of explanation, I know I was marking up this, but I want you to know that these two positions are symmetrical, and I know on the answer sheet, I believe I have the chlorine right there, and it's the same as if I put the chlorine right there. Okay, over here. So, this was sulfonation, chlorination, and I hope you'll remember that this is a Friedel-Crafts alkylation, right? And we have to worry about carbocation shifts when it comes to Friedel-Crafts alkylations. But, so we have a nitro group, meta-directing, deactivating, and if you're wondering if, this should be a no reaction, some teachers might think it's a no reaction. I wasn't really concerned with trying to throw those at you. I just wanted to make sure you got practice seeing meta-directors and ortho-para directors. So this is an absolute meta-director. We will either, we will direct the new alkyl group to one of those positions. And what I like to do is when I see a Friedel-Crafts alkylation, I draw my initial carbocation, whoops, and I ask myself, will this shift, right? Methyl or hydride? And the answer is absolutely it will shift hydride-wise. So I have an H right here. I will shift it over here. And what I'm actually going to be sticking on the benzene ring is this tertiary carbon right there. So this is no longer in our thoughts. It's this right here. So when you do your Friedel-Crafts alkylation, what you'll see in the product, and this is such a popular problem, is you'll see a T-butyl group as opposed to an isobutyl group in your product, okay? And you can see I didn't really space my stuff out that well. Down here, we have an ethoxy group, and we have a sulfonyl group, and you can see we just have acid and heat. So I'm hoping you remember that helper reaction. This helps us, we know we can use sulfonyl groups as blocking groups, and that's amazing. But very frequently on tests, you'll just get a problem where you have a benzene ring with a sulfonyl group, and you'll have acid and heat, and it's just meant to be a removal of sulfonyl. That's all you need to do. So if you get one of these, I would say jump for joy. Easy, 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 easy points, because this is your answer. You just have to wipe away the sulfonyl. Okay, gang, that was part 1. Let's finish off 3 with 4 more. Okay, gang, let's finish up problem 3. Okay, so if we take a gander at the next 4 reactions we have, we can just start right at the top. So we start off with plain old benzene here. So what I hope you're seeing, so no directing groups, right? We can just say fresh slate. We're just going to take the steps as they come. First step, I hope what you're thinking is, I'm going to erase this to give me some room to write. We have a Friedel-Crafts acylation, right? I'll abbreviate that. So remember, with those, no rearrangements, and you stick you stick the piece that you're working with onto the benzene ring right where the carbonyl is, right? Because this is an acid chloride more generically, but we'll stick that carbonyl unit on right there. So, and it doesn't matter where you put it because we have no directing group. So I hope what you see is there's that piece right there, and then I have a carbon, a tertiary carbon with 2 methyl groups off of it. So I have this after step 1. Okay, so step 2, H2 and PDC. Now, we did talk about this in a helper reaction video, and I believe there's even just a dedicated reduction video. But we use this commonly to reduce double bonds, right? Alkenes, alkynes, right? Units of unsaturation, you would call. However, H2PDC also works specifically on carbonyls for the benzylic position only, okay? So if I had a carbonyl over here, the H2PDC would, wipe this away, reduce it, completely gone, but this would remain. So I want to make that very clear, and I think I tried to before, but it's confusing. It's just for the benzylic position only. So after step 2, that is gone. So this is steps 1 and 2, okay? And last but not least, then we end with a sulfonation. So I hope what you saw is we put on a group that was an electron withdrawing group. We then reduce the carbonyl. Now this is just a plain old alkyl group that activates the ring via induction and is an ortho-para director. So now we have an isobutyl group, and now we're going to direct it, para as a result. So our final answer, looks like this, okay? And again, if you had here and here, that's totally fine. What matters is that they are 4 positions apart. Okay, I drew this a little differently on the, than on the worksheet just to give myself some space. So we have O-methyl and we have bromine and we have a nitration going on. Now here's the deal. We have bromine right here. We have O-methyl. They are both electron donating groups. They both direct ortho-para. But you can see that each other's para position is occupied. So the question is, will bromine direct ortho, or will the methoxy group direct ortho? And here's what it comes down to. You defer to the group that activates more. Now you'll never have to decide between like an O-methyl and an NH2 because they're both activating. You can't make that call. However, I think I misspoke. Bromine does not activate the ring. They're both ortho-para directors. That's what I meant to say. So in deciding who directs, right, even though they direct in a similar fashion, bromine deactivates the ring, right? The methoxy group activates the ring. So you defer to the group that actually activates the ring and more strongly, right? So if this was hypothetically, an alkyl group, you would still go with the O-methoxy because the resonance activation is stronger than just hyperconjugation, induction, whatever. Long-winded way of saying you defer to the O-methyl, the methoxy, okay? So we're going to be putting a nitro group on. It's going to be following the methoxy group's orders. Bromine is really just along for the ride, so we have O-methyl, and you can put the nitro group here or here as well, okay? Okay, now here. Now we did talk about this in another, in the one directing group video, but when you have multiple rings or multiple groups. So when we take a look at this, right, we're going to be brominating, that much is clear. But if you take a look, we kind of have 2 groups, but it's weird that it is a ring. Just look at them once at a time. I hope you can see that off this benzene ring, this is a partially positive carbon. It's going to be sucking electron density out of the ring. This is going to be a meta group, and it deactivates, okay? On the other hand, I'm not saying this alkyl group right here is the best activating group out there, but it does activate the ring slightly via hyperconjugation, inductively, right? So if you had to choose between which one is going to, command bromine where to go, it's going to be the group that activates, right? This deactivates, this activates. So basically this is decoration at this point. We need to decide for this position, will we go ortho, 1, 2, or 1, 2, 3, 4, para? And it's absolutely going to be para, right? Minimize that, steric interactions. So, and then bromine up there, okay? 1, 2, 3, 4. There's a para relationship between those 2. And last but not least, I love this problem. Okay, so down here, again, we start with a blank slate in just benzene, right? Now, I hope you see a Friedel-Crafts acylation, right? So I'm even going to use some space over here. I'm going to do my scratch work in black. So I'm going to put this on this carbon. Remember, you just straight up attach the carbonyl carbon in the acid chloride you're given. So there's 1, 2, 3, 4, 5 carbons, and I might run out of space. I have to redraw this over here. So 1, 2, 3, 4, 5, double bond, carbonyl. Let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Perfect. Okay. Second step. Now, here's another look. Remember, there's multiple ways to reduce benzylic carbonyls, right? Carbonyls at the benzene, the benzylic carbon position. Up here, we did it with H2PDC. Down here, we see that zinc, mercury, amalgam, and HCl. That is a Clemmensen reduction, okay? So this is step 1. Step 2 is erasing the carbonyl right there, okay? Now, this last step, H2SO4, kind of, you know, it doesn't really pop out to you. You're like, what reaction did I learn? What happened here? So, kind of just take this back to your OChem 1 knowledge or just generic organic chemistry knowledge. We have acid and we have, we're not going to touch the double bonds in the benzene ring. We know that would mess with the aromaticity, but what's going to happen is we're going to protonate this double bond right here. We know this double bond will grab this in a Markovnikov fashion, and I'll put 3. What's going to happen is we generate a carbocation. Now remember, what carbocation are we going to form? We have the opportunity to form primary or secondary. We're absolutely going to be forming this secondary carbocation, okay? Now what's going to happen, crazily enough, right? If you want to think about it, this, right, is an ortho para director, okay? And I know we usually direct para, but I just want to point this out. The ortho position, should this bond go out and grab this, that would make a 6-membered ring. So this will happen, and I'll draw this up here. I'll draw it in green, or we'll do it in purple. So this was 1, 2, 3, 4, 5, and 6. And I hope you remember that off of 5, we have a methyl group. Right? Right here. Because this carbon right here did not make it inside the ring. It's outside the ring, okay? Now remember, in doing this EAS, I'm kind of giving you the full mechanism. We then create a carbocation at this position up top. And let me just make sure that is what I want to do. Yes, because this carbon made the bond. So remember, to finish this up, this conjugate base will come back. We'll use this H. Swing electrons in there. We'll regain the aromaticity. But what is your final product? Well, your final product is this right here. And I encourage you to work that mechanism out for yourself. But I've seen this question asked so many times. It's, I think everything makes sense up to here. You kind of get like a WTF, like what's going on here situation. And it's really just protonating a double bond and then doing what I would call maybe just even more like a generic like EAS reaction. Not really a name. It's kind of like a Friedel-Crafts in a way, but done in a much different fashion than we've previously seen. Okay? All right, gang, that does it for problem 3. We have one more in 4. I know it's been a gauntlet, but stick with me and let's finish this walkthrough strong. Okay, gang, to wrap this worksheet up, we have problem 4, and it states and tells us that when we do sulfonation with, this is, if you want to use a common name, this is called aniline. I hope I'm not misspelling this. Aniline. Basically, benzene with an amine, an NH2 group, right, with H2SO4 and sulfur trioxide. Weirdly, we get meta-direction, not orthopara. We would absolutely expect orthopara direction because that's an electron donating group. So we need to explain that and then draw the mechanism. So what's going on here? Well, before we even start drawing the mechanism, to explain this change in direct group direction, I hope what you'll, and again, I feel like most frustrating things where you have a core concept that's pretty new and you're learning it and it changes slightly, sometimes acid-base just rears its ugly head again. Acid-base chemistry, that is. We're in a strongly acidic environment here, right? I hope when you see sulfuric acid, you think to yourself that you have an abundance of H+ at your disposal. Well, never, ever, ever forget, nitrogens are very basic. So, ammonia, for example, has a pKa of roughly 35. Remember, low pKa. Low pKa means you're a good acid, a stronger acid. Higher pKa means you're a weak acid. So this is a really, really, really bad acid, which means, right, if you're a weak acid, then you're a strong base. And I'm not saying this is a super strong base. but I'm certainly not saying it's an acid. It's definitely up there in terms of basicity, right? It's a base to reckon with for sure. So this nitrogen has similar basicity, like, you know, we can ballpark it. So given the acidic environment, what's going to happen? And remember, we've talked about how you can protect your amines, right? With you can acetylate them, but in this particular problem, before you do any actual, you know, EAS chemistry, the first thing this nitrogen is going to do, and I'm going to actually do this top right so I don't have more space to draw the mechanism. It is going to grab H plus from sulfuric acid, giving us NH3 plus and the conjugate base right before we even start. So I hope you can see is that alone eliminates its positive charge and then forces it to become a meta-director, okay? Because it will absolutely be sucking electron density out of the ring inductively, right? Because the resonance won't work. We'll break the octet rule. So this is inductively happening. So in terms of the mechanism, right, this is just almost a review of the sulfonation mechanism. So remember, we have sulfur trioxide. The first thing that happens is one of these oxygens gets protonated. It will grab H+, strongly acidic environment, as we've already seen. So that puts a positive charge on sulfur, and remember, we are in the business of putting positive stuff on benzene rings. So then we enter in this. I know I'm switching colors, I apologize. So we then have, I'll just do it all in one color down here now. So we have this. So over here, I can just go ahead and grab the sulfur. Whoop, that's not there anymore. Still have the NH3 up top. Now we have the SO3H down here. We didn't have to, you know, bounce any bonds or anything like that. We just were able to give sulfur a 6 bond, giving it, you know, a neutral formal charge. Now we have a positive charge over here. So remember, what we'll do to regain the aromaticity is we have a proton right there. We'll bring back this, you know, the conjugate base of this sulfuric acid right here, or whatever you like, whatever base you have available to you. We'll grab that. We'll restore the aromaticity of the ring. And I could have absolutely given this problem to you with the NH3 plus right there in the, you know, as the final. Kind of wanted to disguise it. I've seen it, you know, presented that way on exams. So the last thing I would personally draw, and this is reflected on the worksheet, SO3H, is the original. And what I'll do is I'll do NH2 and I'll draw this H over here. The original, this, coming back and deprotonating and giving you the products. Okay, gang, so that finishes the worksheet. If you came in search of answers, I hope you have found them and they are satisfactory. Thank you for using jOeCHEM. If you're watching this video, that means you have financially supported the website. And I just want to take the chance to say thanks. I'm so humbled you're using jOeCHEM as your organic chemistry tool of choice. So glad you're watching this video, and I hope to see you all in the next video.